Hello again, Year 12 Method students. In this video we're going to be looking at stationary points and how we can use calculus to find the positions of stationary points. So when we talk about stationary points in this section, we're really talking about two things. We're talking about turning points, so turning points that can be, I should have given myself more space to write here. So turning points that could be a minimum or a maximum turning point, right? Or we're also talking about stationary points of inflection, and a stationary point of inflection can look like this kind of thing, or could also look like this sort of thing, if you excuse my bad pictures. Now, the key idea here, and so these were points of inflection. Key idea here is that at these stationary points, the gradient of the function for one instant is 0. If you were to draw a tangent line at the minimum turning point, it would have a gradient of 0. It would be a horizontal line. If you were to draw a turning point at a tangent at a maximum turning point, it would have a gradient of 0. It would be a horizontal line. If you were to draw a tangent line at a stationary point of inflection, I should call that stationary, because you can have stationary points of inflection. Sorry, you can have points of inflection that aren't stationary, but here we're talking about stationary points of inflection. Again, if we were to draw a tangent line at these stationary points of inflection, they would have a gradient of 0. Now, if we know that that's the definition of these stationary points, well, that means we can use what we know about gradients to actually identify where these stationary points are on a graph. Because what we can do, so okay, if we know the gradient's meant to be 0, we can find our rule for the gradient, which is the derivative function, and we can let the gradient equal 0. We can let that derivative function equal 0. So let's see how that works. For example 1, we're asked to find the coordinates of any stationary points on the graph of y equals x squared times e to the power of x. Now how that function's going to look, how that graph's going to look may not be obvious to you, but even if we're not sure how the graph's going to look, we can still work out where the stationary points are going to be. So, first job, we're going to find dy dx, right? We're going to find the rule for our gradient at any point. Now, this is, even though it looks like a pretty simple function, it is two functions of x multiplied together. We've got x squared and we've got e to the power of x, which means we can use the product rule to differentiate it. And the product rule says you put down the first thing, so x squared, and then you multiply by the derivative of the second thing. The derivative of e to the power of x, remember, is e to the power of x. And then plus, we put down the second thing, right? So e to the power of x times the derivative of the first thing, right? So this is just applying the product rule, and the derivative of x squared, of course, is 2x. And so we've got a rule for the derivative that says our gradient at any particular point of x is equal to x squared e to the x plus 2x e to the x. Now, we want to know where the stationary points are, and we just talked about that stationary points have a gradient of 0. So if dy dx is representing the gradient, then to find a stationary point, points, we're going to let dy dx equal 0. And so we're going to get x squared e to the x plus 2x e to the x equals 0. Now, if we're trying to solve this and we're not allowed to use our calculator, well, maybe we can try doing some factorizing, right? We've got everything on the left-hand side of the equation. We've got an equals 0. Let's see if we can factorize this. We've got e to the power of x as a common factor of both terms, and we also have x as a common factor of both terms. So we could take out x e to the x, and what we'd be left with is we've got 1x left in that first term, and we've also got a 2 left in the second term, so plus 2. So by the null factor law, we've actually got three factors here, haven't we? We've got either x equals 0, or e to the x equals 0, or x plus 2 equals 0. Now, x can equal 0, that's a solution straight away. E to the power of x equals 0. Remember that there's actually no power of x you can put on a positive base that's going to make it equal 0. If you picture the graph of e to the power of x, it never actually reaches the x-axis. So this is going to have no solution. no solution to that equation. But of course, if x plus 2 equals 0, then that just means x equals negative 2. And so we've got two x coordinates that solve the equation. In other words, there's two values of x where we've got stationary points. We've got a stationary point at x equals 0 and a stationary point at x equals negative 2. Now, always read the question carefully because this one's saying to find the coordinates of any stationary points, which means we need the x coordinates and the y coordinates. We know the x coordinates. If we need the y coordinates, we're going to substitute in, but we're going to substitute into the original rule here, right? Don't sub back into the derivative. The derivative doesn't have y in it. The derivative's got dy dx. If you're trying to find y, you need to sub into the rule that has y in it. So when x equals 0, y equals, so we're going back up here, 0 squared times e to the power of 0. Now, if you're timesing that by 0, you're just going to get 0, right? So we've got a y coordinate of 0. When x equals negative 2, y will equal negative 2 squared e to the power of negative 2 times e to the power of negative 2, which will be, again, I haven't left myself enough room for this example. So negative 2 squared is obviously 4, and we can move e to the power of negative 2. We can move that to the bottom of a fraction. So we can write this as 4 over e to the power of positive 2. And so our stationary point coordinates are 0, 0, from x equals 0, y equals 0, and negative 2, 4 on e squared. Negative 2, 4 on e squared. So these points here are the stationary points on our graph. Right, so even with a function that we may not have been very familiar with that graph, we've been able to identify where the stationary points are using calculus and using the fact that we knew that the stationary points exist where the gradient is equal to 0. All right, here's a second example that's a little bit backwards because this question is actually telling us where the stationary point is. This says the graph of y equals ax squared minus bx has a stationary point at 10, negative 25, and we have to work backwards to find the values of a and b. All right, now this point here actually tells us two things. This point tells us that when x equals 10, y equals negative 25, right? Because we're told that this is a point on the graph. So that's one bit of information that we can use. Second bit of information is that we know that this point here is actually a stationary point, which means that when x equals 10, the gradient, the derivative, which is dy dx, is equal to 0. And so from those two pieces of information, we should be able to generate two different equations that can help us solve for a and b. So let's start with the first one. From 1, when x is 0, y is negative 25. So we can say that negative 25 equals, when x is 10, y is negative 25. So that will equal a times 10 squared minus b times 10. So in other words, negative 25 equals 100a minus 10b. And from the second bit of information we had, we can say that the derivative, so dy dx, which is 2ax minus b. All right, so even though you got a's and b's there, you're still just multiplying by the power of x and subtracting 1 from the power. So there's our derivative. And we said that when x was equal to 10, the derivative was equal to 0. So we're going to let dy dx equal 0 and x equal 10. So 2a times 10 minus b, so that's 20a minus b. Right, and these two equations, we can solve simultaneously to work out a and b. Probably going to start with this one here because I can easily flip this to just say b equals 20a, right? And that's a nice easy one to substitute into the other equation. And so if we let b equal 20a, we're going to get negative 25 equals 100a minus 10 times 20a. All right, so we're substituting that in. And that gives us 100A minus 200A on the right hand side, and so we're going to get negative 25 equals negative 100A, and so A equals negative 25 divided by negative 100, that's going to be 1/4. Right, and then we can come back to what we had here and say, well, if B was equal to 20A, and we now know that A is 1/4, we can say that B is equal to 20 times 1/4, and 1/4 of 20 is 5. So A is 1/4 and B is 5. Go back and read the question carefully. Sometimes you have to write out the full equation, other times you might just have to write down the values of A and B. This one just said determine the values of A and B, and we've done that. We've got A and we've got B, so we're done.